In this video, we're going to look at some examples of calculations with carbon-14 dating. These calculations are fundamentally no different than the other radiometric dating problems that we've done before. The only difference is related to how we find the N0 when we're doing carbon-14 dating. So due to the fact that all living organisms essentially have the same relative amounts of carbon-14, we can use the amount of carbon-14 in a living thing as our N0. And so in this problem, we're told that the amount of carbon-14 is 35% of that. That would be in living trees. And so, again, when we do the percentages, we can assume that the N0 is 100, and then the NT, in this case, will be 35. And so when they want to know how old the tree is, they're asking us to solve for time in the same equation that we've been using. So we have that N0 is going to be 100, NT is going to be 35. So the only thing we need to find the time is K, and I can get K from the half-life. So K so I punch that in my calculator, I get 1.21 times 10 to the negative 4. And again, the units on the rate constant are 1 over the time units. So our half-life was in years, so the units on K are going to be 1 over years. And we'll finish the problem up on the next slide. Okay, so I've collected the information from the previous slide, and now we can take all of this information, plug it into our first equation, and solve for T. So 35 and I'll often use a script T so I don't get it confused with plus signs. So the first thing I'll do is divide both sides by 100. And now I'll take the natural log of both sides. So the natural log of 0.35 is negative 1.05. The ln cancels with the e, and so we bring down what was in the exponent. All right, and my last step, I'll divide both sides by K. All right, and our final answer for the time is 86.76. Of course, we need to put units on that. And so the half-life was in years, the rate constant was in 1 over years, and so our time will be in years. Okay, and I've got one more example. All right, so this one is very similar to the last problem. They're just specifying the amounts of the carbon-14 a little bit differently. Instead of giving me the percentage of carbon-14 that remains, they're giving me the actual activity. And so here's the activity of the object, of the old object. This is the activity of a living organism. So this is my N0. This is my NT. And if you notice, when they talk about the activity, they're specifying that we're looking at 1 gram of this cloth, and we're comparing that to 1 gram of a living organism. So we always need to be using the same amounts of both the old item and the new item that we're comparing to. Because of course, if I use 10 grams of the cloth and compare that to 1 gram of what's in a modern or in a living organism, right, those aren't going to match up. All right, so just to summarize what we know, so I know the N0 is 0.255 becquerels, and T is 0.162 becquerels. And I'll find K the same way I did the last time. And, you know, since we've already done the other problem, in principle, we don't need to solve for K because we can just look back at the work we previously did. But for completeness, I'll go ahead and do it. So K So we again get K to be 1.21 times 10 to the minus 4 years to the minus 1, and we'll finish up the problem on the next slide. All right, so I've again collected the information from the previous slide. We can take all of this, plug it into our equation, solve for t. So I'll again divide by n0. All right, and I'll again take the natural log of both sides. And my last step. And I get T to be 3753. And again, because our half-life was given in years, units on our final answer will be in years.